Hi everyone, welcome to lesson 5 of our permutation combinations unit. Today's lesson is called applications. So basically we're going to work with a few word problems and work with a few diagram problems. To start us off today, we have our opener question. It has, um, if all the letters in the word applications are used, then how many different arrangements are possible that begin with an A, I, or an O? So first off, let's figure out how many letters do we have in total. If I count up my letters, we have 12 letters in total. Let's jot that down as a quick note. We want, out of those 12, to begin a new word with an A, I, or an O. Well, now the question is how many A's, I's, and O's are there? So I see 1, 2, 3, 4, 5 A's, I's, or O's. So I can choose any 5 of those letters to be the very first letter. After that, could be any of the other letters following. So there are 11 other letters after that. To speed things up, I go 11 factorial. As always, I'm going to divide off anything that repeats. I see the letter A repeats, that's dividing off 2 factorial. I see the letter P repeats, that's another 2 factorial. There we go. And the letter I's repeat, and that's also another 2 factorial because there were 2 of each. So once you run this number, we get something as big as 24,948,000, and that's it. There we go. In example B, we have how many 4-letter arrangements are there if letters can be repeated. So basically, we're trying to fill in 1, 2, 3, 4 4-letter arrangements. So out of these 4 slots, what letters do we have? Well, we could be any of these letters here. So usually we're thinking 12 letters. However, it says if the letters can be repeated, so that means there's no difference between this first A or this first A, or this first P or this first P. So it doesn't really matter if we have repetition. So in total, how many letters do we have now? Because of this, we have, I'm going to write a quick note that we have 9 unique letters. So if you have 9 unique letters, all we're going to do is slot in 9, 9, 9, and 9. 9 times 9 times 9 times 9, of course, will get us to 6,561 arrangements. In example 2 here, we have determined the number of different arrangements using all the letters of the word accesses that begin with exactly 2 S's. Well, how many S's do we have in total? We have 3 S's. How many letters do we have in total? It looks like we have 3, 6, 7, 8, 8 letters in total. So I'm going to do a quick note, 8 letters. So we have 8 letters in total. That's just a quick side note there. So we want to begin with exactly 2 S's. So I can do something like this. If I have 8 blank lines, so 1, 2, 3, 4, 5, 6, 7, 8, and I want 2 S's, and of course I only have 3 S's in total, so I can go 3, 2, and those are going to be S and S. So that's an S, that's an S. And this slot here, this is the one that counts. We don't want an S, so I'm going to say not S here because we want exactly 2 S's. If we had an S here, that'd be 3 S's, which wouldn't work for us. So in exactly 2 S's, how many letters are not S's here? Well, we have A, C, C, E, and E, so that's 5 different letters that are not S's there. So we got S, S, not S, and then every other letter will just be whatever's remaining. So you've already used up 3 letters here. How many letters left over? 5, 4, 3, 2, 1. And there we go. So we're going to run this number. This is going to get us 3,600. But most students would stop here, but the one thing we have to remind ourselves of is dividing off repetition. So what repeats? I don't see any A's. I see double C's, so that's 2 factorial. I see double E's, that's 2 factorial, and triple S's, 3 factorial. So once I had this answer here, I'm going to divide off my repetition. This now gets me to 150 options. In example B, we want to begin with at least 2 S's. So that means you have 2 scenarios right now. You have the scenario where you have 2 S's And then you have the scenario that you have all three s's. So let's set these up. So if you have two s's, it's basically going to look the same as the previous example here. So let's just jot that down. You'd have 3 times 2 times 5, and that 5 there represents not s, times 5 factorial ultimately, because that's 5, 4, 3, 2, 1. Dividing off repetition, 2 factorial, 2 factorial, 3 factorial. So again, everything's the same as part A. With at least 2, we want to add on the case where it's 3 s's. Well, if you're 3 s's, you're going to be division statement. It'd be 3 times 2 times 1, because that's all 3 s's, times 5 factorial for the remaining letters, dividing off repetition, 2 factorial, 2 factorial, 3 factorial. There we go. From here, let's evaluate. On the left here, I have 150. On the right there, I have 30. Adding them together, we get a grand total of 180. 180 options. So in part C here's what's the difference in the questions? What's the difference between part A and part B? Well, part A, and maybe I'll type this out instead. A is, so we can say A is only 2 s's. B is 2 or 3 s's. And so that's the main difference in the two cases there. In example 3 here, we have a baseball team with baseball team has 8 players on the field at a time, 3 outfielders, 4 infielders, and 1 pitcher. If there are 5 outfielders, 7 infielders, and 3 pitchers on a team, determine the number of lineups for a baseball team if the outfielder can play any position and the infielders can play any position as well. So the way that we want to set this up is the following. Let's choose our people first, okay? So we're going to do all our choices first. So let's start with the first one here. We have 5 outfielders in total. So we're going to go 5. And you're going to choose any 3 because you have 3 on the field at any time. So we're going to go 5, choose 3. And to this, we're going to multiply that by, well, how many infielders? We have 7 in total. We're going to choose how many of them? We're going to choose 4 of them. So 7 choose 4. Multiplied by 3 pitchers in total, 3 choose, and we have 1 pitcher ever on field at a time, so it's going to be 3 choose 1. From here, we're also going to multiply because we are going to determine their positioning. We can multiply by 3 factorial because that's the 3 outfielders, and 4 factorial because that's the 4 infielders, and they can play in any position there. So once you pick the person, it'll be 3, 2, 1 and a 4, 3, 2, 1 for the people that you picked, and there's only 1 there. So there's only 1 position the pitcher can play. In total, if you run these numbers here on your graphing calculator, because here now we're using the combination function, again, you want to run this on your graphing calculator, we get a total of 151,200 options to set up this team. Moving on, we have algebraically calculate n perm r and n com r. So we have, again, just recalling our two equations here. So permutations, it's just n minus r. Denominator combinations, n minus r, and an extra r factorial after that. So again, just be aware of which equation you're using where. So for this first example here, solve n perm 2, which equals 10,100. Right away, I'm just going to split my screen so that we have some space here to work on each side. So let's set up our equation. So n pick 2 is the same thing as saying n factorial divided by n minus 2 factorial. And of course, that's equal to our answer of 10,100. From here, let's get rid of the factorial. So I'm going to bring down the numerator basically. So I have n times n minus 1 times n minus 2. And we're going to stop at n minus 2 because it matches up with our denominator factorial there. We have a n minus 2 factorial denominator here. Still all equal to 10,100. Our factorials will now officially cancel. Cancel. Leaving us with, and if you want to multiply in, you probably should. I have n squared minus n, and let's move all the numbers to the same side, minus 10, 100, and all that's now equal to 0. From here, you can solve it however you want to solve it, factor or quadratic formula or whatever you can think of. Here I know it's going to be n minus 101 multiplied by n plus 100 equals 0. Let's find n for both. So on the left here we have n equals 101. On the right we have n equals negative 100. And of course you can't ever have this negative 100, so this is my extraneous solution, and my actual solution is 101. Going to example B here, we have n choose 6 equals n choose 5, and the question is, why is that? Why is that occurring? And there we go, trying to scroll. So n choose 6, let's write out that equation, and n choose 5, let's write out that equation. So n choose 6 is going to be n factorial divided by n minus 6 factorial 6 factorial. And on the other side, we have n factorial divided by n minus 5 factorial 5 factorial. Alright. From here we want to try our best to clean up, so I'm just going to write down my factors in full. Factorial in full. Because my numerator is bigger for both, my denominator is smaller, so I'm going to start off with n minus 1, n minus 2, and so on and so on. And I'm stopping here at n minus 6 factorial because I see that same n minus 6 in my denominator to cancel out. Alright, that's all going to be equal to our right hand side here. And there we have it. We have our equation kind of set up. So let's cancel out whatever we can. On the left here in blue, n minus 6 factorials are cancelled out. Over here in green, we have the n minus 5s and n minus 5 factorials cancelled out. From here, I can clean up both sides. So what I'm left with is, and by cleaning up I mean because it's the same on both sides, I'm going to cancel out everything that's the same. So I have 1, 2, 3, 4, and 5. All of those are all the same. So they're all just going to be canceled out over here. So what are we left with? On the left, we still have this n minus 5 that we haven't touched, all divided by 6 factorial. Factorial. And that's all going to be equal to, well, there's nothing in my numerator. It's just going to be 1 over 5 factorial. From here, I believe we can solve for n. So solving for n here, let's get rid of that. Solving for n here, you can multiply out your denominator. So you can get something like 5 factorial, why is that off, minus 5 divided by 6 factorial, which I'm not really just going to write at 6 factorial, but it's going to be 6 multiplied by 5 factorial. And all of that's equal to 1. Why did I change my denominator to 6 multiplied by 5 factorial? Because this and this will cancel out now. So what are you left with? We're left with n minus 5 all divided by 6 equals 1. And again, just isolating for n here, so that's n minus 5 is equal to 6 because you multiplied out the 6, so then n has to equal 11 once you move that 5 over. And there we go. That's our solution. In the next two examples, we're going to do something similar. So here we go. This time we're mixing between permutation and combination. So be careful which equation you're choosing. So on the left, you have n factorial divided by n minus 4 factorial. On the right, we have that 12. That 12, nothing's going to happen to it. So we're just going to leave it outside of a bracket here. Let's call this n factorial divided by n minus 3 factorial, 3 factorial. There we go. From here, we can start to cancel things out and distribute out. So we have on the left n minus 1, n minus 2, n minus 3, and of course n minus 4 factorial. We're going to stop there because it's going to cancel with our denominator, n minus 4 factorial. So let's cancel that out right away. Cancel, cancel. That's equal to, we still have the 12 on the outside. Okay, we still have that 12 on the outside. Then on the inside we have n multiplied by n minus 1, n minus 2, and of course n minus 3 factorial. And that's where we were going to stop. Over n minus 3 factorial. And 3 factorial down here by itself is just 3 times 2, which is just 6 there. Okay, so what can we cancel out over here? N minus 3 factorial, n minus 3 factorial, and I can clean this up as 12 divided by 6, which is eventually 2. Let's cancel out things on both sides that are the same on both sides. So we cancel out n minus 1, n minus 2, because I have an n minus 1, n minus 2 on both sides eventually. So that leaves you with the following. You have n minus 3 equals 12 divided by 6, which is 2. So n here has to equal 5 for this to work out. There we go. And in example D, finally, so again, very, very similar to what we've been doing today. This is just going to take me a bit of space to do, so let's carve out some space here. There we go. So we just separating the page, sorry about that. So let's go and let's write out this equation here. So we have n pick 4, so that's the same thing as saying n factorial divided by n minus 4 factorial. There we go, that's our right hand side. On the left hand side we have that 4 there, and let's set up the n minus 1. That's all in brackets because that's my numerator factorial. My denominator is going to be n minus 1 minus 3, and all of that is now factorial. There we go. Close bracket here. Starting on the left, there's nothing really to do yet. Let's clean up the right side before we start messing around with both sides. So we'd have n factorial divided by n minus 4 factorial. That's all equal to 4. Still on the outside of a, we have n minus 1 numerator factorial and a denominator of n minus 4 factorial. There we go, close bracket there. So here, let's start bringing stuff out. So again, our numerator here would go n minus 1, all the way up to n minus 3 ultimately, n minus 2, and n minus 3. The n minus 4 factorial, n minus 4 factorial will cancel out, so that's all I have left on the left side. On the right side, again, something similar here. You can have 4 multiplied by the n minus 1, n minus 2, n minus 3, and you'd stop here because n minus 4 factorial and n minus 4 in the factorial in the denominator would cancel out as well. So once you're here, we can drop off any common factors. So n minus 1, 2, 3, all gone, 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 because it's the same on both sides. So what are you ultimately left with? You're left with n equals positive 4. we go.